Okay, a question all about dynamic equilibrium. First question, sulfur trioxide is produced by reacting sulfur dioxide with oxygen. This reaction is done in industry at 1 to 2 atmospheres and reaches dynamic equilibrium. Yeah. Okay, explain the effect on the rate of attainment of equilibrium if the reaction is done at a higher temperature than 2 atmospheres, for 3 marks. Okay, this is a good example of making sure you read the question, okay? It's easy to think that this question might be getting into if you increase the pressure, what happens to the position of equilibrium? You know, if you increase the pressure, then it goes to the side with the least number of particles, and if you increase temperature, it goes in the endothermic direction, all that stuff. But you won't get any marks for that because the question says, explain the effect on the rate of attainment of equilibrium. It's not asking about the position of equilibrium stuff, so it's easy to answer the wrong question, okay? So the take-home message is, read the question and make sure you're answering what they ask. So that's the first thing, okay? And the second thing is, getting 3 marks out of this is difficult, right? Explain the effect on the rate of attainment of equilibrium if the reaction is done at a higher pressure than 2 atmospheres. Well, this is how you've got to extract 3 marks, okay? So, first thing, if you've got a higher pressure, then first thing to say, the molecules move close together because they're more concentrated. Molecules closer together because they're more concentrated. Okay? But it might be better to say just the other way around. The molecules are more concentrated, therefore they move closer together. Generally, in explanations, it's better to say therefore rather than because. If you can put, rather than saying the answer because this, it's better to say this, therefore this, and therefore the answer. Just generally, that produces nicer, better structured answers. But I've done it the wrong way around there. I said molecules closer together because they're more concentrated. But it's fine. Okay. Right, so now we can say therefore, write out the word, you have to write out the word, I'm doing it shorthand, okay? Therefore you get more frequent collisions. Okay? And therefore, the time to reach equilibrium, time to equilibrium is reduced. Okay? So that is the sort of things you have to say to extract 3 marks out of this question. And I know that's not easy in an exam. So we'll move on soon, but I know I keep banging on about this, but to extract 3 marks out of something that's not easy, you just have to say the obvious things and use your knowledge, okay? So it's talking higher pressure. What do you know if you increase the pressure? Well, you know that it becomes more concentrated. So write that down, even though it might seem obvious, okay? And you know that if it's more concentrated, the molecules move close together. Write it down. You'll probably be, you know, at least a 2 mark stage by that point. So just don't worry about saying things that you think might be obvious. There's a good chance you get a mark. So therefore, more frequent collisions. Therefore, time to equilibrium is reduced. Okay? And again, last time I'll say this, it's talking about the time to equilibrium. It's not talking about the equilibrium position. So read the question. Okay, let's move on. Right, what volume of oxygen in cm cubed would react completely with 500 cm cubed of sulfur dioxide? Okay, sulfur dioxide, they're telling us that there's 500 cm cubed of that. It wants to know what volume of oxygen will react with that. To do these questions, you need to look at the big number in front of the chemical expression for the thing. And that wasn't brilliantly put, but that's sulfur dioxide, okay? And that's oxygen. Look at the big number in front of the formula. And we've got a 2 there, and there's nothing there, which means it's an invisible 1, okay? It's like having 1 O2. So, that means that for every 2 molecules of SO2, there's 1 molecule of O2. So 2 molecules of SO2 react with every 1 molecule of O2. Now, with gases, there's a 1-to-1 relationship between the volume of the gas and the number of molecules in it. It doesn't matter what the gas is. We're like 1 meter cubed of SO2 will contain the same number of molecules as 1 meter cubed of O2. So it's the same with volume of gas. It'll be 2 to 1, which means that there's 2 to 1, so 2 to 1, so it's 500 cm cubed divided by 2 of O2. Happy with that? Okay, so that's it. 500 divided by 2, which is, as you know, 250. So 500 cm cubed of SO2 will react with 250 cm cubed of O2. Okay, that's a molar ratio, if you like. It's a 2 to 1 molar ratio. Okay, when there are alternative methods of producing a product, the final pathway is chosen by considering atom economy, cost of energy, yield of product, and rates of reaction. State another factor that should also be considered. 1 mark. This is a difficult question, okay? I wouldn't blame you for not being able to think of anything else in an exam. But if you look at the mark scheme, what they're looking for is equilibrium position or usefulness of byproducts. So that's not easy to think up, okay? So remember it now, okay? So when scientists are deciding how to make something in industry, just remember right now, let's list them. The things they need to worry about are atom economy, cost of energy, yield of product, rates of reaction, equilibrium position, and usefulness of byproducts. Just remember that list and regurgitate it, okay? Right, last bit, the Haber process. The reaction between nitrogen and hydrogen is exothermic. Yes, it is. Let's do this in blue. Okay, so we've got N2, that's 1 molecule of nitrogen, plus 3 molecules of hydrogen, is in a reversible reaction to make ammonia. Makes 2 molecules of NH3, okay? That's called the Haber process. It's how we make ammonia in industry. If nitrogen and hydrogen were reacted at 150 atmospheres pressure and 300 degrees C without a catalyst, some ammonia would be formed, okay? In the Haber process, a pressure of 150 atmospheres and 450 degrees C and an iron catalyst is used. Okay, if you didn't know those reaction conditions for the Haber process, learn them now. Haber process always comes up, okay? You have to know this. This is done at 150 atmospheres, 450 degrees C, and with an iron catalyst. Okay? Those are the optimum conditions. Although sometimes it's taught as 200 atmospheres. Between 150 and 200 atmospheres is fine, okay? It's a very high pressure. Right. Explain why the conditions used in the Haber process are better than the first set of conditions for the manufacture of ammonia. 6 marks. Right. So what they're telling us is this, okay? The bad conditions that they first listed, so bad conditions were 300 degrees C, okay, 150 atmospheres, and no iron catalyst, right? The good conditions, and these are the ones that you need to learn, 450 degrees C, they've used the same pressure, so it's asking about temperature. We don't have to talk about pressure because it's the same, and an iron catalyst, okay? So learn those conditions right now. Right, so the question was, explain why these conditions, the ones that are actually used, are better than these conditions for 6 marks. Right, so you need to know how it's all about position of equilibrium and changing pressure and temperature, okay? So very important, learn this, it will come up in your exam. Right, so let's start with a catalyst. Why is it good to have a catalyst? Right, first thing, the mark scheme for this question and this specimen paper is wrong. There's one thing they said, which is a cardinal sin, right? In the mark scheme, they said that catalyst lowers the activation energy. No, it doesn't. Never write that, okay? Catalysts do not lower the activation energy, okay? What a catalyst does, a catalyst provides an alternative reaction pathway with a lower activation energy, okay? And there's a difference. So learn that right now. Never write catalysts, a catalyst lowers the activation energy. That's wrong. What you should write is, a catalyst provides an alternative reaction pathway with a lower activation energy. Okay, so that's the first thing. So, that would be a good thing to start with. So write, a catalyst provides an alternative reaction pathway with a lower activation energy. Okay, probably got a mark straight away, 1 out of 6. Good. Therefore, actually, I'm going to write it out because I want to encourage you to use the word therefore rather than because. Okay, therefore, a catalyst increases the rates of both, okay, don't forget this, the forward and reactions, of both the forward and backward reactions, forward and back reactions. Okay, so if you have a lower activation energy, you've got this new alternative pathway that the iron provides with a lower activation energy, that will increase the rate of both the forward and back reactions. Okay, this double arrow means it's in equilibrium. It means the reaction can go that way or that way. That's the forward reaction, that's the backward reaction. Okay, and a catalyst will increase the rate of both of them. Good. Therefore, the reaction reaches equilibrium faster. Okay, we're just churning out our knowledge of catalysts at this point. You're going to pick up 2 or 3 marks just doing this. We've answered it, okay? We've used our knowledge, we said this, therefore, the reaction reaches equilibrium faster. But throw in a bit of knowledge, you might pick up a mark. So what we're going to throw in is our knowledge that catalysts don't affect the yield or the equilibrium position. catalyst does not affect the yield or the position of equilibrium. Okay? So if you didn't know that, learn that now. When you use a catalyst, it doesn't increase the yield and it doesn't affect the position of equilibrium. It doesn't shift it one way or the other. Catalysts provide an alternative reaction pathway with a lower activation energy, therefore they increase the rate of both the forward and backward reactions, therefore the reaction reaches equilibrium faster. Okay? So, we've covered catalysts, we've used our knowledge, we've just got down on the paper as much as we can. And so that's why it's better to use a catalyst, because it reaches equilibrium faster. Okay, now let's talk about temperature. We're not going to talk about pressure because it's the same. This is asking about temperature. I'm going to cover pressure at the end to make sure you know it, but now it's temperature. And I need to clean the board. Okay, so why don't I do temperature in a different colour? Let's do it in yellowy green. Okay. Good, so we've covered the catalyst. Now, why do we do this reaction at 450 and not 300? Okay. So, this is where we start talking about how temperature affects position of equilibrium. So, listen carefully, you really need to know this. Higher temperatures, okay, so 450 is higher than 300. Higher temperatures favour the endothermic reaction. What does that mean? Okay, now at the very beginning of this question, it told you that the reaction between nitrogen and hydrogen is exothermic. What does that mean? So, nitrogen and hydrogen, the reaction is exothermic. It means there's heat being released in that direction, okay? The reaction between nitrogen and hydrogen is exothermic. So, write plus heat down on the correct side like I did, okay? Get in that habit. That will really help you. Now the knowledge bit. You just need to learn that higher temperatures, when you've got this double arrow, that pushes the position of equilibrium onto the side where there isn't heat. In other words, the endothermic direction, okay? That direction, when these two react together, that forward arrow there to make this, that releases heat. That's the exothermic direction, okay? So that is the exothermic direction, but in this direction is the endothermic direction, okay? And learn right now that higher temperatures favour the endothermic reaction. So, that means by doing it at 450 rather than 300, it's pushing the position of equilibrium in that direction, okay? Right, so let's get that down. Get some marks. Right, we'll start with just writing down what you know. That higher temperatures favour the endothermic reaction. Thermic reaction. Okay? Got another mark just by writing that down. Okay. Therefore, the position of equilibrium moves to the left. Okay? Now, we're trying to make this stuff. We want ammonia. But we've just done it at a higher temperature and pushed the reaction in the wrong direction, okay? Why do we do that? Well, we'll get to that in a minute, but you need to point that out. So, therefore, you get a lower yield of ammonia. Okay? Like I say, that's bad, right? So why on earth are we doing this? Well, we'll cover that now and nail the full 6 marks. Okay? Right, so the reason we do it is this. At a higher temperature, it's this stuff again. Sorry, not that stuff. The stuff we talked about here that I rubbed out. If you have a higher temperature, so higher temperature means molecules move faster. Obvious, right? But write it down. You might get a mark. You probably will. Okay? Therefore, more frequent collisions. Okay? Use your knowledge again. Therefore, not only do you have more frequent collisions, but more of the collisions have a high enough energy to cause a reaction to happen. Therefore, more collisions. We're talking about collisions between the nitrogen and the hydrogen. Therefore, more collisions with high enough energy for a reaction to take place to form a molecule of ammonia. That's also known as a successful reaction, if you like. You can use that language. Okay? And therefore, there's a higher reaction rate. Do you see what I mean about using the word therefore rather than because? If you use the word because, you have to go in this direction, and it's ugly. If you say this happens, therefore this, therefore this, therefore this, you end up nicely with your conclusion. Okay? And now, we're going to finish off the whole thing with one little flourish, nail the 6 marks, and really show the examiner you know what you're talking about. The whole point of this, like we talked about here, this bit, we deliberately do it at a high temperature and do something that apparently is not going to help us. We're pushing the reaction in that direction and lowering the yield, but the reason we do it at that high temperature is to get a higher reaction rate. Okay? And a higher reaction rate is worth getting at the expense of a lower yield. That's the whole point. Okay? If you can communicate your understanding of that to the examiner, brilliant. That is what you need to do. Okay? So yes, we do have a lower yield by doing it at a high temperature, but it's better to have a lower yield and a higher reaction rate, okay? Because the higher temperature gives us a higher reaction rate because of what we talked about. So, remember this sentence right now. I'll write it out in full, tattoo it on your brain, and just regurgitate it in the exam. It is better to have a higher reaction rate at the expense of a lower yield. Okay? It is better to have a higher reaction rate at the expense of a lower yield. Okay? And the reason is, yes, you might have a lower yield of this, but the reaction is happening so much faster, we're still getting plenty of that, getting a lot more of that out. Okay. So that is how you would get 6 marks. All of this you would definitely get 6 marks for this question, okay? Learn this, it's very important for your exams, the Haber process, and understanding the position of equilibrium stuff is very important. Good. Now I said, so we've finished the question at this point, okay? But I want to make sure you understand about pressure as well and how that works. So I'm going to talk about that briefly now, okay? So again, I'm just going to rub out the board, won't be a sec. Okay, so how does pressure work? Right, it's like this. It's quite simply that if you increase the pressure, it moves the position of equilibrium to the side with fewer molecules or fewer moles. What does that mean? Okay. You have to count the number of molecules on each side first. And to do that, you look at the big numbers in front of each molecule. Okay? Ignore the little numbers. The big numbers determines the number of each molecule. So that's just N2. So that means there's an invisible 1 there. It's just 1 molecule of nitrogen. 3H2, that means there's 3 molecules of hydrogen. Okay? So on the left, there's a total of 4 molecules. On the right, it's 2 ammonias. So there's 2 molecules on the right. Okay? And that's how you do it. So, like I said, if you increase the pressure, it moves the position of equilibrium to the side with the fewer molecules, which is that side. Okay? So it favours that reaction in this case. Got it? And that's it. So likewise, if you decrease the pressure, it will favour that reaction. If you decrease pressure, it will favour the reaction that produces more molecules. Okay, so let's summarise how this position of equilibrium stuff works for temperature and pressure. For temperature, like we covered in the first part, higher temperatures favour the endothermic reaction. Endothermic. Okay? That's that direction. Likewise, if you lower the temperature, it'll push the position of equilibrium in the exothermic direction. So lower temperatures favour the exothermic reaction. Okay? And higher pressures favour the reaction that produces fewer molecules. Okay? 4-2, so higher pressures favour that reaction. Okay? The forward reaction in this case. And lower pressures favour the reaction that produces more molecules. So if you lowered the pressure, it will push your position of equilibrium in that direction. And that's it. Learn those two right now. You've got to understand this stuff. There you go. And that's it. Position of equilibrium.